All right. Hello, everyone. My name is Ray Garner, and welcome to this year's Public Astronomy Lectures. The goal with this year's, as opposed to what last year's was, this year I want to be way more organized, way more cohesive, and way more interactive. I want to ask y'all questions. I want y'all to ask me questions during the talk, if you can. I want to make it way more of a beginner's level kind of stuff. Last year, it was pretty much whatever I wanted to talk about at whatever level I felt comfortable talking at, which wasn't necessarily helpful for everyone else. There's some topics that I did kind of higher level stuff. There's some topics that kind of went really basic. And so this year, I want to treat this series as like an Astronomy 101 course that you would take at college. So hopefully that means every week we'll build off of the weeks previous. We'll talk about things in a way more cohesive structure. And I hope you guys will like it. So to start off this kind of Astronomy 101 series, the best place to start is with just a basic introduction to the universe. And I hope to start each of these talks with a little quote relating to what we're going to talk about. And this week's quote is a little bit of a downer. It's from Neil Armstrong, first man to step foot on the moon. He said, "It suddenly struck me that that tiny pea, pretty and blue, was the Earth. I put up my thumb and shut one eye, and my thumb blotted out the planet Earth. I didn't feel like a giant. I felt very, very small." So for most of human history, our ancestors imagined Earth to be stationary at the center of a relatively small universe. These ideas, of course, made sense at the time when understanding was built upon everyday experience. After all, we cannot feel the constant motion of Earth as it rotates on its axis and orbits the sun. And if you look at the sky every night, night after night, you'll see that the sun, the moon, and the planets all appear to revolve around us each day. Nevertheless, we know now that the Earth is a planet orbiting a rather average star in a rather typical galaxy in a vast universe. The historical path to this knowledge was long and complex. We'll soon see in later weeks that the ancient belief in an Earth-centered universe changed only when people were confronted by strong evidence to the contrary. And we'll explore how the method of learning that we call science enabled us to acquire this evidence. But first, it's useful to have a general picture of the universe as we know it today. So take a look at this beautiful photo from the Hubble Space Telescope. This is called the Hubble Ultra Deep Field Image. This photo shows a piece of the sky so small that you could block your view of it with a grain of sand held at arm's length. Yet it encompasses an almost unimaginable expanse of both space and time. Nearly every object within it is a galaxy filled with billions of stars. And some of the smaller smudges are galaxies so far away that their light has taken billions of years to reach us. So let's begin our study of astronomy by exploring what a photo like this one tells us about our own place in the universe. So the galaxies that we see here are just one of several key levels of structure in our universe, all illustrated sort of in our cosmic address. Our cosmic address, rightfully so, starts off with Earth. Earth is a planet in our solar system, which consists of the sun, the planets and their moons, from closest to farthest, Mercury, Venus, Earth, Mars, then the asteroid belt, where Ceres, the largest dwarf planet in the asteroid belt, is, Jupiter, Saturn, Uranus, Neptune, and then the Kuiper belt objects, where objects like Pluto, Makemake, Eris, and tons of other objects are located. I've already mentioned some of those countless smaller objects. Those include the rocky asteroids and the icy comets. And keep in mind that our sun is a star, just like the stars we see in our night sky. Our solar system belongs to the huge disc-shaped collection of stars called the Milky Way Galaxy. A galaxy is, of course, a great island of stars in space, all held together by gravity and orbiting a common center. The Milky Way is a relatively large galaxy containing more than 100 billion stars, and many of these stars are orbited by planets. Our solar system is located a little over halfway from the galactic center to the edge of the galactic disk. Billions of other galaxies are scattered throughout space. Some galaxies are fairly isolated, but most are found in groups. Our Milky Way, for example, is one of the two largest among more than 70 galaxies, most relatively small, that make up the local group. Groups of galaxies with many more large members are often called galaxy clusters. On a very large scale, galaxies and galaxy clusters appear to be arranged in giant chains and sheets with huge voids between them. The regions in which galaxies and galaxy clusters are most tightly packed are called superclusters, which are essentially clusters of galaxy clusters. Our local group is located in the outskirts of the local supercluster, which was recently named Laniakea, which is Hawaiian for immense heaven. Together, all these structures make up our universe. In other words, the universe is the sum total of all matter and energy, encompassing the superclusters and voids and everything within them. Now, I could read off to you the sizes of these different levels of our cosmic address. The Earth is about 10,000 kilometers across. The Milky Way Galaxy is about 10 to the power of 18 kilometers. But once we get to these truly astronomical distances, kilometers is a very bad unit of measurement for astronomy. So just take this for instance. The nearest star, which of course is the sun, is about 150 million kilometers away, or about 93 million miles. The next nearest star is Proxima Centauri, which is about 40 trillion kilometers away. And the nearest big galaxy is Andromeda, at a distance of 24 quintillion kilometers. And those numbers, sure, they make sense, but our brains do not do well with the biggest numbers. So how do we actually make sense of these numbers? We do that by using two different strategies. So the first strategy is scientific notation. I will be like throwing formulas at you or equations. That's not what the goal of this is. But you will see scientific notation written throughout these weeks, and it's important for you to have a grasp on what that is. So scientific notation refers to powers of 10. So 1 power is 10 to the power of 1, which is just 10. 2 powers is 10 squared, or 10 to the power of 2, or 10 times 10, so 100. 6 powers, 10 to the 6, is 10 times 10 times 10 times 10 times 10 times 10, or a million. When it's a positive number, when the power is a positive number, think of that number as the number of zeros you've got to add after 10. So 1 million has 6 zeros after that initial 1, so it's 10 to the power of 6. For negative powers, think of dividing. So 10 to the minus 1 is 1 divided by 10, or 0.1. 10 to the minus 2 is 1 divided by 100, or 0.01. And 10 to the minus 6 is 1 divided by a million, or 0.000001. Think of that, a power to the minus, as the number of times the decimal place has to move to the left. So 10 to the minus 6 has 5 zeros in front of that 1 after the decimal point. Any number can be expressed this way. So if we go back to that slide with the distances to the nearest stars and galaxies, we can rewrite them in a much more compact way. So the distance to the sun, instead of being 150 million kilometers, is 1.5 times 10 to the 8 kilometers. The distance to Proxima Centauri, instead of being 40 trillion kilometers, it's 4 times 10 to the 13 kilometers. And the distance to Andromeda, instead of being 24 quintillion kilometers, it's 2.4 times 10 to the 19 kilometers. So that's one method we astronomers and other scientists use to handle these really big and really small numbers. The other strategy, and this is really only for astronomy, is we define new units. All sciences define new units, but these units are important for astronomy. So one you'll see pretty immediately are astronomical units, or AUs. An astronomical unit is 1 Earth-Sun distance. So 1 AU is 150 million kilometers. So we would talk about the distance to other planets, like Jupiter. Jupiter is 5.2 AU away from the sun, which immediately tells you it is 5.2 times further away from the sun than the Earth is. However, astronomical units are really only useful within the solar system, on solar system scales. Once we get outside the solar system, and we'll talk about galaxies much further along, stars and galaxies much further along, we need to get a bigger unit. And that bigger unit we'll use is a light year, the distance light travels in 1 year. Now, it is a common misconception that light year is not a unit of time. It is a unit of distance. It's the distance light travels in 1 year. The way we get that is we know the speed of light is about 300,000 kilometers per second. 1 year is about 31,500,000 seconds, or about 3.15 times 10 to the 7 seconds. If you're in astronomy class, a good way to remember the number of seconds in a year is it's pi times 10 to the 7 seconds. So to get a light year, you simply take these two and multiply them together. You can see it worked out there. You get a light year is about 10 to the 14 kilometers, or about 100 trillion kilometers. So it's a big, big distance. You can also talk about light days, light minutes, which are just the distance light travels in a day, a minute, etc. So 1 AU is about 8 light minutes. So that means that light from the sun takes about 8 minutes for it to reach Earth. So let's think about a light year and the speed light travels, which is extremely fast by Earth standards. It's so fast that if you made light go in circles, it could circle Earth nearly 8 times in a single second. Nevertheless, even light takes time to travel the vast distances in space. Light takes a little more than a second to reach Earth from the moon and about 8 minutes to reach Earth from the sun. Stars are so far away that their light takes years to reach us, which is why we measure their distances in light years. So imagine the sun that blew up just now. Of course it didn't, but you can wait and maybe we'll find out in a hot sec. When would we know? Well, the sun is about 8 light minutes away from us. So that means it would take about 8 minutes for any of that information to reach the Earth. We'd be in blissful ignorance for 8 minutes. So keep an eye on the clock. Maybe in 8 minutes, the sun will get information that the sun did blow up. Probably didn't. It won't. But you can always check me. I might have magic powers. Imagine an alien civilization around the nearest star, Proxima Centauri, and they were using a very powerful telescope to observe the Earth. Who would they see as president of the United States? Now, here's your hint. Proxima Centauri is 4.3 light years away. Well, about 4.3 years ago on Earth, we would be seeing the last months of the President Obama's term in office. In fact, I think right now, Proxima Centauri is seeing Election Day 2016. So what they're really seeing is a bunch of happy people and a bunch of sad people. And they'll just have to wait for what happens over the next 4 years. Imagine galaxies in this, imagine aliens in this particular galaxy, NGC 4845. That NGC stands for New General Catalog. It's just a database of important space objects. But imagine aliens in that galaxy were using an impossibly powerful, like actually physics wouldn't allow this telescope to exist, but they were using an impossibly powerful telescope to observe the Earth. What life forms would they see? Now here's your another hint. NGC 4845 is 65 million light years away. So aliens in that galaxy looking towards Earth would not see humans wandering around. They would see the dying days of the dinosaurs. So this general idea that light takes time to travel through space leads us to this remarkable fact, that the farther away we look in distance, the further back we look in time. So take this picture of the Andromeda Galaxy. It is about 2.5 million light years away, which means we see it as it looked about 2.5 million years ago. We see more distant galaxies as they were even further in the past. Some of the galaxies in that Hubble Deep Field image were more than 12 billion light years away, meaning that we saw them as they were more than 12 billion years ago. But it's also amazing to realize that any snapshot of a distant galaxy is a picture of both space and time. For example, because the Andromeda Galaxy is about 100,000 light years in diameter, the light we currently see from the far side of the galaxy must have left on its journey to us some 100,000 years before the light we see from the near side. Therefore, images like this show different parts of the galaxy spread over a time period of 100,000 years. When we study the universe, that means it is impossible to separate space and time. That's a thought that I was just amazed by. Even though I do this professionally, that just completely blew my mind, that I forgot about that when we look at galaxies, we're seeing the image is also sort of warped by time there. And as we'll discuss later, the measured age of the universe is about 14 billion years. And this fact, combined with the fact that looking deep into space means looking far back in time, this places a limit on the portion of the universe we can see. So look at this image here at the bottom of the slide. If we look at a galaxy that is 7 billion light years away, we see it as it looked 7 billion years ago, which means we see it as it was when the universe was half of its current age. If we look at a galaxy that is 12 billion light years away, we see it as it was 12 billion years ago, when the universe is only 2 billion years old. Excuse me. And if we try to look beyond 14 billion light years, we'd be looking to a time more than 14 billion years ago, which is before the universe existed, and therefore means that there is nothing to see. That means that the distance of 14 billion light years marks the boundary or the horizon of our observable universe, the portion of the entire universe that we can potentially observe. However, this does not actually put a limit on the size of the entire universe, which we assume to be far larger than what we can observe. We simply cannot see or study anything beyond the bounds of our observable universe because the light from such distances has not had time to reach us in a 14 billion year old universe. So, that's a lot of information to kind of delve into, but now we're going to try and talk about how big the universe is. And one way to do that is with scale models. So what we're going to do is we're going to start with the solar system, something way more easy to comprehend at first than the entire universe. So let's imagine that the sun has been shrunken down to the size of a grapefruit, about 14 centimeters across. So here are some questions for you then. If the sun is a grapefruit, on this scale, how big is the Earth? Is golf ball size, marble, a pinhead, just an unimaginably tiny speck? And on this scale, how far away is the sun? Is it a foot away, a meter, or about a yard? 15 meters, or about 3 car lengths? Or 100 meters, about a football field away? Now, if you're watching this live, I would put this in a poll in Zoom. But if you're watching this on video, pause the video, think about it for a second. Seriously, think about it for a second, and come back to this video when you've got an answer. So now that you've got an answer, this is the rest of the solar system on that scale. The Earth, if you answered the size of a pinhead, you're correct. And if you answered about 15 meters or 3 car lengths away from the sun, that is also correct. You see the relative sizes of some of the planets. So Mercury and Mars are about the size of a sand grain. They're pretty tiny. Venus and Earth are about the same size in actuality. So they're going to be the same object of a pinhead. Jupiter and Saturn are slightly larger at a marble. Uranus and Neptune, you imagine a pea. Pluto is just an unimaginably tiny speck. And then the nearest star to us, Proxima Centauri, is about the size of a grape. Now, one of my professors does a wonderful way for you to visualize this. He puts the solar system on the campus of Case Western Reserve University. But since I imagine many of you aren't actually familiar with Case Western Reserve University's campus, what I've done is I've placed the sun at the center of the fountains in Centennial Olympic Park in Atlanta. So if you do that, put it in that center middle ring, the entire inner solar system all fits within the fountain area. You don't have to walk very far. So next time you're visiting the fountains with, a grapefruit, some sand grains, and some pinheads in your pocket, you can just walk around and drop them off, and you can see, you can compare everything. However, once you get to the outer solar system, that is where you've got to start walking a bit further. So in the center of this image is still the inner solar system, but you see you've got to at least cross the street, start walking into the actual park to put Jupiter down, put a marble for Jupiter. Further on into the Centennial Olympic Park for Saturn, another marble. Almost to the Coca-Cola Museum, right up here, you put down a P for Uranus. Conveniently, the planet Neptune, named after the Roman god of the sea, is somewhere in the Georgia Aquarium. Very convenient. Pluto, that tiny speck, is almost at the Mercedes-Benz stadium. However, the nearest star is not even in Atlanta. It's not even in Georgia. Hell, it's not even in the United States. The nearest star, Proxima Centauri, is somewhere in the Northwest Territories of Canada. So while I could encourage you to walk and place the solar system down in Centennial Olympic Park, I do not encourage you to walk across the border, walk across Canada and the United States to go place a grape down somewhere in the Northwest Territories. Also, for context, the farthest man-made satellite that we've ever sent is Voyager 1. It's reached about 152 billion kilometers, billion miles away from the sun. On this scale, Voyager 1, of course, is just like an atom. But Voyager 1 has just now made it to Georgia Tech in Midtown Atlanta. Remember, Voyager 1 was launched in the 70s. So it's had 40, 50 years to travel almost. And it has not made it even outside the perimeter of Atlanta, which is kind of insane. Now, this kind of separation between our sun and Proxima Centauri is typical of the separations between star systems in our region of the Milky Way Galaxy. Therefore, if you want to represent the Milky Way on such a scale, we cannot use the same scale. This is a 1 to 10 billion scale. Instead, we've got to shrink it by another factor of a billion. So the scale is now in 1 to 10 to the 19. So on this new scale, each light year becomes a millimeter. And the 100,000 light year diameter of the Milky Way Galaxy becomes 100 meters, or about the length of an American football field. Visualize a football field in your head with a scale model of our galaxy centered over midfield. Our entire solar system is a microscopic dot located around the 20-yard line. The 4.4 light year separation between our solar system and Proxima Centauri becomes just 4.4 millimeters on this scale, smaller than the width of your little finger. If you stood at the position of our solar system in this model, millions of star systems would lie within reach of your arms. But another way to put the galaxy into perspective is to consider its number of stars, more than 100 billion. So imagine tonight that you're having trouble sleeping, perhaps because sadly my lecture tonight has put you into a sense of existential terror. So instead of counting sheep to help you fall asleep, you decide to start counting the stars in the Milky Way. Even if you were able to count about one star each second, it would take you 100 billion seconds, or about 3,000 years, to count them all. You would need thousands of years just to count the stars in the Milky Way Galaxy. And that assumes you never take a break. No eating, no sleeping, and certainly no dying. But as incredible as our Milky Way may seem, the Milky Way is just one of roughly 100 billion galaxies in the observable universe. Just as it would take thousands of years to count every star in the Milky Way, it would take thousands of years to count all the galaxies. But think for a moment about the total number of stars in all these galaxies. If we assume about 100 billion stars per galaxy, then the total number of stars in the observable universe is roughly 100 billion times 100 billion, or 10 to the power of 22. So how big is that number? Imagine going to a beach. Run your hands through the fine-grained sand and count each tiny grain of sand as it slips through your fingers. Then imagine counting every grain of sand on the beach and continuing to count every grain of dry sand on every beach on Earth. If you could actually complete this task, you would find that the number of grains of sand is comparable to the number of stars in the observable universe. That is how big that number is. So hopefully I've now given you a sense of how big the universe is. But our universe is vast not only in space, but also in time. So now let's stop talking about how big the universe is, but talk about how the history of the universe and how we understand it today. But before we begin, you may wonder how we can claim to know anything about what the universe was like in the distant past. We'll talk about that throughout the rest of these talks, but you already know part of the answer. Because looking farther into space means looking further back in time, we can actually see parts of the universe as they were long ago, simply by looking far enough away. In other words, our telescopes are somewhat like time machines, enabling us to observe the history of the universe. So let's start with the beginning. So telescopic observations of distant galaxies show that the entire universe is expanding, meaning that the average distances between galaxies is increasing with time. This fact implies that galaxies must have been closer together in the past, and if we go back far enough, we must reach the point at which the expansion began. And we call this beginning the Big Bang. And scientists use the observed rate of expansion to calculate that it occurred about 14 billion years ago. The universe as a whole has continued to expand ever since the Big Bang, but you don't have to worry about, us rapidly becoming farther apart from each other physically. Because on smaller scales, the force of gravity has drawn matter together. So if you take a look at this image, for example, look back towards the very beginning, the Big Bang, you see that the pinkish gas is kind of evenly distributed throughout the universe. But as you come forward in the diagram, come to where the Hubble Space Telescope was pointing, you see that matter has become more clumped. Gravity has pulled that gas to form stars, galaxies, planets, and of course us. So we don't have to worry about, being expanded away from each other by the universe. Most galaxies, including our own Milky Way, formed within the first billion years after the Big Bang. And within galaxies, like the Milky Way, gravity drives the collapse of clouds of gas and dust to form stars and planets. Stars, of course, are not living organisms, but they do go through a life cycle, as you can see here in this lovely diagram. A star is born when gravity compresses the material in a cloud to the point at which the center becomes dense enough and hot enough to generate energy by nuclear fusion, the process in which lightweight atomic nuclei smash together and fuse to make heavier nuclei. If the star lives, as long as it can shine with energy from fusion, and dies when it exhausts its usable fuel. So you see here in this image, the star is being born in the nebula at about 9 o'clock in this image, as gravity pulls that gas together into a dust cloud, then a globule. We'll talk more about what those are much later. We eventually, the temperatures get so hot in the center that fusion is able to start to get a protostar and then a main sequence star. And it will last like that for billions of years as it runs out of its fuel. And when it runs out, in its final death throes, a star will blow all of its content back out into outer space. The most massive stars die in titanic explosions called supernovae, which are seen about 5 o'clock here on this diagram. Excuse me. The return matter mixes with other matter floating between the stars and the galaxy, eventually becoming part of new clouds of gas and dust from which new generations of stars are born. Galaxies therefore function as cosmic recycling plants, recycling material expelled from dying stars into new generations of stars and planets. Our own solar system is a product of many generations of such recycling. And the recycling of stellar material is connected to our existence in an even deeper way. By studying stars at different ages, we have learned that the early universe contained only the simplest chemical elements: hydrogen, helium, and a trace amount of lithium. We on Earth are made primarily of other elements such as carbon, nitrogen, oxygen, and iron. So where do these other elements come from? Well, evidence shows that they were manufactured by stars, some through nuclear fusion that makes stars shine, and others through nuclear reactions accompanying the explosions that end stellar lives. By the time that our solar system formed, about 4.5 billion years ago, earlier generations of stars had already converted up to 2% of our galaxy's original hydrogen and helium into heavier elements. Therefore, the cloud that gave birth to our solar system was made of roughly 98% hydrogen and helium and 2% other elements. You'll learn later, astronomers just call everything that isn't hydrogen and helium a metal. This 2% may sound small, but it was more than enough to make the small rocky planets of our solar system, including the Earth. On Earth, some of these elements became the raw ingredients of life, which ultimately blossomed into the great diversity of life that we see today. So when I say that we are in this universe, we're observing this universe, yes, but we are also actually a part of this universe. We are made from star stuff, as Carl Sagan so creatively said all those years ago. So now that we have sort of a history of the universe, now let's put that on a scale, just like we did with the sizes of the universe. And a great way to do that is to put the 14 billion year age of the universe onto a year-long calendar, on this cosmic calendar. So on this cosmic calendar, the Big Bang starts on the first instant of January 1st, and the present is the stroke of midnight on December 31st. So on this scale, the Milky Way Galaxy probably started to form around May. Uh, by late September, life on Earth was flourishing. However, for most of Earth's history, living organisms remained relatively primitive and microscopic. It wasn't until December that we even got multicellular life. Early dinosaurs appeared on Christmas. And by a few days later, December 30th, the dinosaurs are extinct and mammals took control of the Earth. Around 9 p.m. on December 31st, humans, the first early humans, started to walk upright in what would later become Africa. Perhaps the most astonishing fact about the cosmic calendar is that the entire history of human civilization falls into just the last half minute. The ancient Egyptians built the pyramids only about 11 seconds ago on this scale. About a second ago, Kepler and Galileo proved that the Earth orbits the sun rather than vice versa. The average college student was born about 0.05 seconds ago, around 11:59, 59.95 p.m. On the scale of cosmic time, the human species is the youngest of infants, and a human lifetime is a mere blink of an eye. And that's absolutely wild to think about. So, now throughout this talk, you have probably just been sitting here listening to me, watching me, and think that you're just kind of sitting there. But of course, nothing could be further from the truth. As you sit on spaceship Earth, which was coined by the inventor and philosopher R. Buckminster Fuller, you are in fact being spun in a circle as Earth rotates. You are racing around the sun in Earth's orbit. You are circling the galactic center with our sun, and you are careening through the cosmos in the Milky Way Galaxy. So now let's explore all of those motions in a little bit more detail. So the most basic motions are the Earth's rotation, its daily rotation, and its yearly orbit around the sun. So Earth, hopefully you didn't need me to tell you this, but Earth rotates once each day around its axis, which is the imaginary line connecting the north and south poles through the center. Earth rotates west to east, counterclockwise if you look down at the Earth from above the North Pole, which is why the sun and the stars appear to rise in the east and set in the west each day. Although the physical effects of rotation are so subtle that our ancestors, and sadly some people today, assume the heavens revolved around us, the rotation speed is quite substantial. Unless you're very close to the north or south poles, you are whirling around Earth's axis at a speed of more than 1,000 kilometers per hour or 600 miles per hour, which is faster than most airplanes. But at the same time as this rotation on its axis, Earth also orbits the sun, completing one orbit each year. Once again, hopefully you didn't need me to tell you that. Earth's orbital distance varies slightly over the course of each year, but as we discussed earlier, the average distance is 1 astronomical unit, which is about 150 million kilometers. Again, even though we don't feel its motion, the speed is impressive. We are racing around the sun at a speed in excess of 103,000 kilometers per hour, or about 60,000 miles per hour, which is faster than any spacecraft yet launched. Now look at that figure in the lower left, and I'll point some things out that will be very important in the coming weeks. So notice that the Earth's orbit defines a flat plane, this kind of blue sheet in the figure, that we call the ecliptic plane. Earth's axis is tilted 23.5 degrees perpendicular to the ecliptic plane. The axis tilt happens to be oriented so that the axis points almost directly at a star called Polaris, or the North Star. But keep in mind that the idea of an axis tilt only makes sense in relation to the ecliptic plane. In space, there's no up, down, there's no left, right, sideways. In space, up and down mean only away or toward the center of the Earth, respectively. Notice also that the Earth orbits the sun in the same direction that it rotates on its axis, counterclockwise as viewed from above the North Pole. This is not a coincidence, but a consequence of the way our planet was born. As we'll discuss in the coming weeks, strong evidence indicates that the Earth and other planets were born in a spinning disk of gas that surrounded our sun as it formed, and Earth rotates and orbits in the same direction that that disk was spinning. Now, zooming out beyond just our Earth's motions, we can now talk about the sun's motions. There are two major components to our motion in the galaxy. And we'll begin with the motion relative to other stars in our local solar neighborhood, by which we mean the region of the sun and nearby stars. Excuse me. To get a sense of the size of our local solar neighborhood relative to the galaxy, imagine drawing a tiny dot on this painting of the galaxy. Because the galaxy contains at least 100 billion stars, even a dot that is 10,000 times smaller than the whole painting will cover a region representing more than 10 million stars. We usually think of our local solar neighborhood as a region containing just a few thousand to a few million of the nearest stars. Looking at the sun's motion relative to these nearby stars, we see that we are also moving at about 70,000 kilometers per hour, about 40,000 miles per hour, relative to these stars, about 3 times as fast as the International Space Station orbits the Earth. Given this high speed, you might wonder why we don't see stars racing around our sky. The answer lies in their vast distances from us. You probably noticed just in your daily life, if you see an airplane in the sky, the further away the airplane is, the slower it appears to move along the sky. Stars are so far away that even at speeds of 70,000 kilometers per hour, their motions would be unnoticeable to the naked eye, becoming noticeable only if we watch them for literal thousands of years. That's why the patterns in the sky that we call the constellations seem to remain fixed. But nevertheless, in 10,000 years, they'll be a little bit different, and certainly in 500,000 years, they'll be unrecognizable. If you could watch a time-lapse movie made over millions of years, you would see stars racing across our sky. And now, we're going to talk about the next level of motion. So it's best if you understand it like this. If you look closely at leaves floating in a stream, their motions relative to one another might appear random, just like the motions of stars in our local solar neighborhood. But when you widen your view to not just look at the leaves, but also happen to notice that stream, they're all being carried down, you would see that they're all going in the same general direction, despite their random motions relative to each other. In the same way, as we widen our view away from the local solar neighborhood, the seemingly random motions of its stars give way to a simpler and even faster motion, the rotation of the Milky Way Galaxy. Our solar system, located about 27,000 light years from the galactic center, completes one orbit of the galaxy in about 230 million years. Even if you could watch from outside our galaxy, this motion would be unnoticeable to your naked eye. However, if you calculate the speed of our solar system as we orbit the center of the galaxy, you will find that it is close to 800,000 kilometers per hour, or about 500,000 miles per hour. Now, monitoring this rotation is very important because it has revealed one of the greatest mysteries in science. Stars at different distances from the galactic center orbit at different speeds, and we can learn how mass is distributed in the galaxy by measuring these speeds. Such studies indicate that the stars in the disk of the galaxy represent only the tip of the iceberg compared to the mass of the entire galaxy. Most of the mass of the galaxy seems to be located in outside the visible disk, occupying the galactic halo that surrounds and encompasses the disk. But the matter that makes up this mass is completely invisible to our telescopes. We therefore know very little about the nature of this matter, which we creatively have called dark matter. Studies of other galaxies indicate that they are also made mostly of dark matter, which means this mysterious matter significantly outweighs the ordinary matter that makes up planets and stars. This also means that dark matter must be the dominant source of gravity that has led to the formation of galaxies, clusters, and superclusters. We know even less about the mysterious dark energy that astronomers first recognized when they discovered the expansion of the universe is actually getting faster with time, and that scientists have since found to make up the majority of the total energy content of the universe. We'll talk about both of those things way later on. We'll just give you a little bit of taste of all the mysteries of the cosmos. Now, the Milky Way is obviously not the only galaxy in the universe. Within the local group, which here is a beautiful two-scale diagram of the galaxies in the local group. At the center of it is the Milky Way with its host of satellite galaxies. The next largest one is Andromeda, just to the upper left of the Milky Way. Within this local group, some of the galaxies move toward us, some move away from us, and some numerous small galaxies apparently orbit our Milky Way. Again, the speeds are enormous by earthly standards. For example, the Milky Way and Andromeda galaxies are moving toward each other at about 300,000 kilometers per hour, or 180,000 miles per hour. Despite this high speed, we needn't worry about a collision anytime soon. You're not going to gradually see Andromeda getting closer in the sky night after night. Even if the Milky Way and Andromeda galaxies are approaching each other head on, it will be literal billions of years before any collision actually begins. But when we look outside the local group, however, we find two astonishing facts noted in the 1920s by Edwin Hubble, for whom the Hubble Space Telescope is named. He noted that one, virtually every galaxy outside the local group is moving away from us. And two, the more distant the galaxy, the faster it appears to be racing away. These facts might make you think that the universe knew about the current plague before we did and is racing away from us, trying not to get COVID. But there's a much more natural explanation. The entire universe is expanding. We'll save the details for much later, but you can get the basic idea by looking at this diagram. So imagine this blue circle is a balloon, and you've drawn with a permanent marker something, a couple of dots on the balloon. We'll talk about A, B, and C here, those pink dots. Now, as you blow air into the balloon, those dots will appear to move away. Now, obviously, the dots aren't actually moving to a different physical spot on the balloon surface, but instead the balloon is expanding. The latex of the balloon is being stretched, which is causing those dots, despite not physically moving, they'll appear to move across the surface of the balloon. That is not exactly, that is a great analogy to how the universe is expanding. The galaxies aren't physically moving away from each other, but instead the space between them is expanding, causing them to appear to be physically moving away from each other. Now, this analogy kind of breaks down when you ask in the universe, what is the air in this balloon? What's the corresponding thing in the universe? That's what the analogy breaks down. Don't think too hard about it, but it's a good kind of conceptual idea here. So these are all of the motions that we're constantly going through. In fact, in the past hour, past 45 minutes likely, you have moved about 1,000 kilometers along the Earth's rotation, 103,000 kilometers along the Earth's orbit, 70,000 kilometers with respect to the nearest stars, 800,000 kilometers along the sun's orbit, and 300,000 kilometers towards the Andromeda galaxy. Spaceship Earth is certainly carrying us on a remarkable journey. And in relatively few slides here, I've hopefully laid out a fairly complete overview of the modern scientific ideas about the universe. But my goal here is not just for you to be able to recite these ideas. Rather, I want you to understand the evidence that supports them and the extraordinary story of how they developed. And that brings us to astronomy is a human adventure, in the sense that it affects everyone, even those who have never ever looked at the night sky in their lifetimes. Because the history of astronomy has been so deeply intertwined with the development of civilization. Revolutions in astronomy have gone hand in hand with the revolutions in science and technology that have shaped modern life. Witness the repercussions of the Copernican revolution, which showed us that Earth is not the center of the universe, but rather just one planet orbiting the sun. This revolution, which we'll talk about in I think about 2 weeks, began when Copernicus published his idea of a sun-centered solar system in 1543. Three later figures, Tycho Brahe, Johannes Kepler, and Galileo Galilei, provided the key evidence that eventually led to wide acceptance of the Copernican idea. The revolution culminated with Isaac Newton's uncovering of the laws of motion and gravity. Newton's work, in turn, became the foundation of physics that helped fuel the Industrial Revolution. More recently, the development of space travel and computer revolution have helped fuel tremendous progress in astronomy. We've sent probes to all the planets in our solar system, and many of our most powerful observatories, including the Hubble Space Telescope, reside in space. On the ground, computer design and control have led to tremendous growth in the size and power of telescopes. Many of these efforts and the achievements they spawned led to profound social change. The most famous example is the fate of Galileo, whom the Vatican put under house arrest in 1633 for his claims that Earth orbits the sun. Although the church soon recognized that Galileo was right, he was only formally vindicated in 1992 with a statement by Pope John Paul II. In the meantime, his case spurred great debate in religious circles and profoundly influenced both theological and scientific thinking. As we progress through these series of lectures, I want you to try and keep the context of the human adventure in mind. You'll then be learning not only about astronomy, but also about one of the great forces that has shaped our modern world. These forces will obviously continue to play a role in our future. What will it mean to us when we learn the nature of dark matter and dark energy? How will our view of Earth change when we learn whether life is common or rare in the universe? Only time may answer these questions, but the lectures ahead will hopefully give you the foundation you need to understand how we changed from a primitive people looking at patterns in the night sky to a civilization capable of asking deep questions about our existence. So that's the end of this little topic. I did want to give you a look ahead at all the stuff that I hope to cover over the coming weeks. You might have noticed me looking down. Yes, I am reading from something. And this book here walks us through everything. Hopefully, we'll cover all of it. Maybe not celestial timing. That seems to be a little boring. These first couple of weeks, next week, we'll talk about the night sky, what you can see in the night sky, terms and things like that. And the next couple of weeks will be kind of boring. We'll talk about the history of astronomy, motion, energy, and gravity, light and matter, and telescopes. But all of that is very important for you to understand the science of astronomy and the evidence we've collected. We'll spend then a bunch of time talking about the solar system and including some time talking about exoplanets, which I've yet to talk about in any lecture. Then I'll hopefully try and introduce you to special and general relativity, though we'll see how well that goes. And then we'll get into stars and galaxies, and then the life, death, and life in the universe. So thank you for coming, and I hope to see you next week or in the next video.